Right, I guess I'm recording. So Friedyl Crafts is going to come back again here with a couple kind of challenges that pop up with it. So if you remember, we've got the alkylation and the acylation. The alkylation as a requirement required a superactive nucleophile so that when you formed that carbocation, it would then react with the aromatic ring. The acylation, because the electrophile is a little bit more stable due to that resonance, we don't need a superactive nucleophile, so we don't have to activate it. So we get all rings working. As we just discussed with our activating versus deactivating, one of the things that makes them active is if they had a lone pair of electrons. So nitrogen would be a great activating group. The problem with nitrogen, as we've discussed in other units, is that nitrogen is really willing to share those electrons with pretty much anything. And that becomes an issue because in Friedyl Crafts, we have the aluminum trichloride as a Lewis acid catalyst. Well, Lewis acids react with Lewis bases, and that nitrogen's a pretty good Lewis base. Why does that become an issue? Well, if it actually reacts, or not, everything fails today, it can coordinate the aluminum trichloride. And what we end up getting is this complex where that nitrogen is now positively charged. Why is that an issue? Well, if it's positively charged, you just deactivated the ring, right? And so the amine is not a good, or aniline as a starting material is not a good substituent when looking at Friedyl Crafts reactions, because the Friedyl Crafts Lewis acid catalyst will react with it instead and then neutralize all the reactivity. So it's a little bit of a problem to watch out for. Be surprised if it showed up, but nuances. So in this case, we would get no reaction. Potentially more problematic and more relevant would be another issue with our alkylation versus our acylations. Now that we have an idea of multiple substitutions, let's say we ran the reaction, okay? And in this case, we're using anisole as our starting material, and that anisole has that oxygen. Oxygen has that lone pair of electrons. Those aren't as good at donating to the Lewis acid. Remember, nitrogen's a little bit better at that. Why? Oxygen's more electronegative, so it's going to hold those electrons just a little bit tighter, okay? Preventing that Lewis acid catalyst issue. Since it is an activator, this would work great for the alkylation, okay? So great, we would expect the para substitution because it's an activator. Activators are para-orthodirecting, and we would expect the para substitution. We'd have the methyl there. But let's take a look at that ring a little bit closer now. So we now have two things floating around in solution. Okay, we've got and if we have a lot of stuff, we have the starting material that hasn't reacted all of it yet. We have some product, and then we still have the catalyst in between. Well, that catalyst is going to react with the most active nucleophile. Right, well, which one's the most active? We now actually have two nucleophiles. We have the product as a nucleophile, and we have the starting material as a nucleophile. Okay, when we're talking about substitutions, the more active the ring is, the more likely it will react. Okay, that's what we did with our electrophiles. We made them more electrophilic by reacting them with Lewis acids to withdraw some of that electron density. The same thing's going to happen with our nucleophiles. And if we go through and look at this, in the alkylation, that new substituent I just put on there, that CH3, that carbon has more electrons than hydrogen, so this is activating. And our starting functional group was activating, which means if I look at this and compare these two materials, that product is actually more activating than the starting material. That means when my catalyst gets it on to give me that positive carbon, my electrophile, it's going to react with the product, right? Which means we would expect another substitution. That substitution We'll talk about a little bit later as to why it's going to happen up here, where we'd get the substitution at the ortho position to the oxygen. Well, now we have yet another activating group. Well, dang, with another activating group, that product is even more active, and we would encounter the multi-substitution. And this is a common problem with Friedyl Crafts alkylations. Okay? Each of those alkyl groups activates the ring, so we end up getting more and more and more substitution. So really the best option would be, I didn't click, what are you doing? Would be to kind of avoid that issue altogether, and that's where you would move to the acylation. In the case of the acylation, remember we're not adding CH3Cl, we'd be adding CH3 carbonyl Cl. When we run the one reaction, or our first reaction, we would then be putting on this carbon, but it would have the carbonyl. Okay? That carbon now has less electrons than the hydrogen because it is partially positive due to the electronegativity of that oxygen. Okay? That means it is deactivated. So the product has an activator and a deactivator. The starting material just has an activator. We would expect this to only happen once. Okay? So the acylation occurs once, which could be one of the benefits of doing an acylation over an alkylation. How would you get it down to carbons? Because let's say you wanted just carbons. Okay? If I wanted just a, whoa, that was sloppy. Let's say I wanted 2 carbons down there. I wanted that to be an ethyl. How could I get the ethyl if I had the acylation? Okay, well, what's happening there? That reaction would be a reduction. What reagents could I use to do a reduction of a carbonyl? I would just need to go back and reflect back on my reduction reagents from past lectures. We could be looking at hydrogen and platinum, or palladium or nickel. We could be doing the words are escaping me, which is great right now. Claisen. We could be running the Claisen reaction. We could be running the Wolff-Kitchener reduction. We could, not Claisen, Wolff-Kitchener, Clemenson. Clemenson's the word I'm looking for. And we could even potentially do Raney nickel. So there's a lot of different ways that we could reduce away that oxygen, and that way it minimizes this issue with multiple substitutions. So why would we ever pick the alkylation? Well, maybe I want multiple substitutions. It's all really going to depend on the system that you're looking at, and maybe we want multiple substitution. Alkylation's the way to go. If I only want one, probably want to run an acylation. And so with that, we've covered the big kind of issues that could potentially pop up with our Friedyl Crafts. To give you a quick overview on that, we talked about the amine. The amine is not a good material, starting material for any Friedyl Crafts reaction, alkylation or acylation. And then the alkylation gets multiple substitutions. The acylation does one. So we've covered our basics for our Friedyl Crafts, and I don't think we'll ever have to talk about that one again. Cool being at the end of the semester.